Hi, good evening. Can you see my screen and can you hear me?
Yes, sir.
Okay. So this is the ninth week of the tutorial classes for fundamentals of power electronics, which are originally instructed by Professor L. Umanand of IISc Bangalore. So this week, as you can see, I've written here is the isolated DC-DC converters. Second week. Last week, now we had another session for isolated DC-DC converters where we have studied flyback and forward converters. In this session, what we will study is kind of another class of isolated DC-DC converters, which are push-pull types. So there are push-pull converters. Uh, there is half bridge converter and full bridge converter. So these three converters mostly we will study, and we will see why this name push pull is given to this class of converters. Because only two students are present as of now. So a brief recap about forward converter, because we will look back to it for some concepts, is that we studied something called the reset circuitry of forward converter, right?
Sir.
If you're not going to say something, please mute yourself.
Yes, I want to say something.
Yeah, what is it?
Sir, this half bridge, full bridge, and push pull,
Hmm.
they are commonly called as push pull. Is it, sir?
No, it is not like that, but they have something in common,
Oh,
and for that, the name that push pull comes at applies for all of them.
oh.
So,
In
yeah,
the magnetic, sir. Or,
in the magnetics, yes.
okay.
So, reset circuitry, we saw that if we have uh, if we have an ideal transformer means its magnetizing inductance Lm tends to infinity. In other words, it does not draw any current from the it doesn't draw any magnetizing current from the supply. That is, if you have an ideal transformer like this, and if you connect it to an AC source in this fashion, and if the secondary is open circuit, this will not draw any current from the source. But we are making practical converters here, so we cannot have a transformer which has infinitely large matrix inductance. We will try to design it in such a fashion that Lm is very large, but uh, that cannot be infinite. Okay. Another thing is that if Lm is very large, but obviously if it is not infinite, then it will draw some current from the supply. And what will happen in a in a forward converter, when you turn on this switch, then the magnetizing inductance will draw current, and this will be stored as magnetic energy, nothing but half Li squared in the core or in the air gap. The energy sharing depends on the reluctance of the circuit. Now this stored energy that needs to be either dissipated or sent back to the source, for which we need a reset circuitry that we have studied. Now, why I am saying all these things is that one kind of forward converter I wanted to discuss, only to give you the topology, that does not require a reset circuitry. Okay, so forget the converter for now, just think this as an, okay, I will draw the circuit. This is a very common configuration where you want to excite an inductor or a coil for certain period, and when the excitation is uh, when the excitation is withdrawn, you want the stored energy to go back to the supply. This kind of configuration is used a lot in such cases. So forget converter or transformer, anything, simply take it an as an inductor. Okay, now you see, when we turn on, when we want to excite the inductor, here is the supply voltage, say I call it Vin. When you turn on the want to excite the inductor, you turn on both S1 and S2, you close both S1 and S2 together. What will happen is that will cause a current to flow like this. Okay, a current will flow like this. Let us say it's only an inductor, so what you will get is, if I draw IL, I will increase linearly this. Now when you turn off S1 and S2, if I draw S1 S2, so S1 S2 was on during this duration. Now when you turn off S1 S2, when you open S1 S2, what will happen is the inductor was carrying a current in this direction, right? The current will not stop immediately, it cannot, because it is an inductor. So the current will take a path like this. It will go through these diodes, through the source, come back through this diode like this. So it will complete its path like this. So basically the stored energy in the inductor is going back to the supply. So it will be like this. Okay, it will be like this. So if you look at the inductor voltage, if you look at the inductor voltage, that is say V in when they are on, and minus V in when it is off. Clearly you cannot have a duty ratio more than 50% in this case. If you have, then that will cause the staircase saturation of the inductor. Now this same circuit I will draw once again. I will just draw the diodes. Yeah, sorry. I will just draw the diodes on my left hand side so that I can easily draw the transformer. Now this is the primary winding of the transformer of a forward converter. Okay, same circuit I will draw once again, only thing is the diodes I will draw on my left hand side like this, and this is the secondary of the forward converter. See, now okay, I have to draw the dots. In DC-DC converter, if you do not give dots in the circuitry, that doesn't make any sense in the transformers. Now if I draw the magnetizing inductance also here in this fashion, now you see whatever explanation I gave in the last circuitry, everything goes valid here. So the magnetizing current, the load current will anyway, whatever load current is coming, that is getting reflected here, that all will do, that is not a problem in any case, in any way. But the stored energy in the magnetics, or the current in the magnetizing winding, okay, the magnetizing current that now has a path to go back. It will go back to the source. So how will it go back? When you turn off the switches, it will go back through these diodes. It will go back through the source. This path it will take. So in this way, the magnetizing winding that charges and discharges due to the voltage V in only. And the simple duty ratio duty ratio restriction that you have here is D less than 0.5. So if you compare this with our conventional forward converter um, topology, what advantages do you have? You can have higher duty ratio, right? That is not a very big advantage, because there also you can have it if you adjust n1 and n3 like that. But the biggest advantage that we get here is that no need of reset winding, no need of reset winding, right? And there is advantage. Any other advantage? I don't see as of now. But the disadvantage is more switches, more switches. So this is one kind of forward converter that I wanted to show. But now if you see, uh, the magnetizing inductance current Im that flows for both forward converter and flyback converter, that is unipolar, right? Like this only. Sorry, this Im, this is nothing but a reflection of Bm. Okay, let me not write it like this. It may look like Im by Bm, Im or Bm. So not Bm, B in the core, right? Because we know that psi is Li, whereas psi is n phi, and that is nothing but n Ba. So as long as mm you are in the linear zone, that is as long as your L is not a function of current I, then you can say that whatever I will look like, the waveform of B will be the same. You get the B. Now you see, mm, this increment in current, this increment in current, how is it defined? V, whatever voltage V, that generally the V in. Okay, V in equals Lm delta Im by turn on time dts generally. So it is defined by this. But the peak, so the peak of it, the Bm, that is defined by the, that is defined by the core, right? So if you want to have a larger current, more, say for more power, if you have larger, if you want a larger current, hence larger flux, you have to go for a bigger core where you will get more cross-sectional area, so that you can accommodate more flux in it. But the thing is, the what I am saying is, if I look at the BH curve, let us uh, let us ignore hysteresis for the time. It is like this, right? It's like this. What we are doing, we are operating in this zone. So we have designed it so that it can go up to the knee point. In this zone it operates, right? But the thing is, BH is not only in this half, it is like this. BH is like this, and this part is linear too. this part is also linear. So why not use this one also? What will happen is if we utilize the other half of the BH curve, then we can have a current like this. Then we can have a current like this. So you see, you can put it in this fashion that your delta I now increases, or you can now have a larger delta I. You can now have a larger delta I. Or in other words, for the same delta I, if you look here, psi is Li. For the same delta I, your psi reduces. So you can reduce the area of the core so that you can maintain the same amount of P max. Or in other words, if you can have a current like this in a converter, your magnetics become less bulkier, or in other words, the utilization of the core is increased, it is doubled. This is where the push-pull converter comes into play. It pushes and pulls the magnetic circuit on both the sides. So all the uh, converters that we will look at today, uh, we will see that the cores experience flux that is bipolar, unlike that in forward and flyback converters. Okay, so
Sir,
yeah.
sir, can you repeat what you said just now, that if the delta I increases here?
Say we are trying to compare two situations, previous one and this one. Okay, so we have to keep something in common, then only we can compare. So let us let us keep the delta I common. It is, let's keep this constant. Okay, if you keep it common, then this equation is it remains the same. Say I am operating at same duty ratio, same LM and everything, same voltage. But you see what is happening is, for the same delta I, my delta psi is also same, because delta psi is L times delta I. Delta psi is also same. But if you look at the peak value, positive and negative peaks, that is halved. If this the flux linkage corresponding to this was psi 1, then it is here, it is psi 1 by 2 here, which corresponds to a flux, say, equals n phi 1 by 2, right? So now what is happening at full load, I need lesser flux, the flux is halved, and I did not operate it below the knee. I can below the knee point of the BH curve, I can keep it, I can design the magnetic such that at peak load it operates at this knee point. So if my flux has reduced and my flux density be a area of core, this is called phi, if this has halved, if flux has halved, I can make the area of the core half, keeping the B same. B is a material property, right? B max, material property, how much I can go. So we can have a smaller core. We can have a smaller core because the core is now much more utilized. It is being, flux is being pushed in both directions, positive and negative. So all the circuits that we will study today,
Sir,
yeah.
if we in the BH curve, if we operate on both the sides of the horizontal axis,
Mhm.
then the delta I, if by keeping the delta I same, we can reduce the size of the core.
Yes, which also means that we are increasing the utilization of the core. The core is now better utilized. Right, we will need, so you will see that all the converters that we will study today will have this secondary. So I will draw it once and copy later. Yeah. Yeah, please mute yourself. Your question is done. Well, okay. So let us draw the first converter for today, which is push pull, the regular push pull converter. So this will be the secondary for all of us.
Sir,
Yeah, yeah,
before starting on this, I want to ask you a question.
yeah.
Sir, this LM, this magnetizing inductance is the one where this energy, entire energy in the magnetic is stored, right, sir?
Hmm.
Sir, is there any relation between the LM and the dimension of the core?
Um, this thing we discussed. No, I think last week's class was all about that only. Sorry. I said now that LM, the magnetizing inductance. See, if you have a transformer, suppose you have a transformer. Yeah, please mute yourself. I will answer.
Okay.
Suppose you have a transformer like this, two winding transformer. Okay, this, right? Now what you do is you open this secondary side or the other side. So you have two sides, one, two. You open this side too. Do not connect anything here. And this other side you can connect to a circuit, and this will simply act as an inductor, right? This simply act as an inductor. Nothing but this is nothing but a solenoid. I'm talking about practical transformers. So what is the inductance value? That inductance value is nothing but Lm. That is nothing but Lm. Now, what is L? Inductance. Inductance is n squared permeance. Right. Now, what is permeance? Permeance is completely a geometrical parameter. It is given by mu naught mu r, not L, A by L. It's a completely geometrical parameter, which is the. So when I say geometrical parameter, geometry of what? Geometry of the core. So for electrical circuits, we study such things. Now, say if you have an electrical circuit, there are several things inside, and there is two port here. So what is the resistance of the circuit that you see from here?
Yes.
Right. So what we get, we find out the open circuit voltage and the short circuit current, and their ratio is the resistance that is seen from the port. The same thing is there in magnetic circuit also. You can have several limbs in the core, say like this. I'm drawing a very simple one. Maybe there is one air gap here, there is no air gap here, maybe another air gap here, maybe there is another cut here. Let us say, let us make this more like this. Okay, this whole thing is a magnetic circuit. Now you put your coil somewhere. Now once you put the coil somewhere, it sees some reluctance from here. So whatever reluctance it is, and this coil has got some number of turns n, the inductance of this coil will be simply n squared divided by that reluctance r. Now what you are asking, whether it depends on the permeance, depends on the volume of the core. It does, because you see, um, there are two things. If you look at this air gap, say for the first case I consider uh, ideal core. Ideal core means what? Mu r tends to infinity. That means the whole reluctance is being offered by the air gaps only. Then also you see, if you look at the, say, at this portion of the core, it comes like this. So I'm looking at 1 year gap. Okay, it looks like this. So you see the area of the air gap, that also, we are not talking about any fringing. Okay, no fringing. So the area of the air gap, we simply take the core of area of the core as the area of the air gap, like that only, because the flux is flowing in this way. Now if in the other case, if you consider non-ideal, non-ideal mu, say mu or maybe somewhere, say 2000, it is also very large mu or, but now you can also calculate the permeance offered by the, or the reluctance offered by the core. Now again, that will depend on the area of the core. Now how much length, say along the flux has to flow along this path, so what is the length of this path, this path, this path, it will everything. So this whole geometry that decides the permeance that this coil sees sitting here. Okay,
Okay.
now whatever number of turns you have, so permeance times n squared, that will give you the inductance. So it is a function of not only the dimension of the course but also the material that is being used, mu r.
Sir, in a way we can say, if the secondary is open circuited, this the inductance whatever we are measuring on the primary is like a self inductance.
Yes,
Okay. So if we want to make this LM high, just the dimensions that A and L has to be made more and lesser. A has to be increased and L has to be decreased so that
lm, if you want to make high, you can increase the number of turns. You can sort two methods so as to increase the permeance, use thicker and larger cores,
mm,
you'll get more and more inductance. But where we will need it, we will need larger lm in case of flyback converters, because we want it to store energy.
store
For
energy.
forward converter, we will want as small lm as possible,
Yeah. Okay.
because that will make, you see what is happening. We have a reset winding. Okay, so with the reset winding, or maybe with this topology also, everything looks very fine, that okay, we had a problem of energy storage. But please mute yourself. We have a problem of energy storage, but that is somehow sorted out by using this reset circuitry. Hmm, everything is fine, but the problem is, you see, when the switches are closed, there is, if I draw, say, power, when the switch is closed, the supply voltage, that's the voltage that supplies some power. Okay, and when the switches are opened, some of the power are fed back to it, some energy stored is fed back to it. Now whenever you have in any system a bidirectional flow of power at steady state, okay, that in every period some power is fed back, this is nothing but reactive power. Okay, now say this v in, this may be a battery, this may be another power electronic converter, maybe another rectifier. So rectifier cannot handle negative current, so you will need a capacitor. So what will happen is that power that you are giving back, that may be solving your problem in flyback, but that is creating another problem from your source side, right? So larger lm you have means every cycle you are storing more and more energy, means every cycle, I mean every cycle larger lm means stored energy in every cycle is more, so the power that you are giving back is more. So the va capability of the dc source, that is increasing, or in other words power factor is deteriorating. That is why lm, not for this forward converter, for but for any transformer, we want it to be infinitely, um, yes, infinitely large, if not as high as possible. But
Sir,
yeah.
actually, when we are storing back the energy,
Hmm.
suppose to a capacitor
Hmm.
on the input side, then it leads to an increase in voltage, because we are actually transferring a voltage, sorry, energy in the inductor to energy in the capacitor.
No, it's being stored in the inductor. It's being stored in the core, and that energy is given by half Li squared. So voltage does not increase. Voltage is stiff anyway from the source side. Current increases
No, while discharging, sir.
while discharging.
Uh,
Oh, okay. If you have a capacitor, is that will increase the voltage of the capacitor.
okay.
So there will be a ripple in the capacitor voltage. Now, depending on how much ripple you desire in that, I mean, that will give you the value of the capacitor. That is how we will calculate the required value of capacitor that you need there.
So you said that the VA rating of the source increase.
Yeah.
Uh, what do you mean by that, sir? It is
Volt
apparent
ampere
power.
rating.
It is
Apparent power.
okay, sir.
All right. So, mm, this is the secondary. I will keep a copy of it. Yeah. Now, this is the regular push-pull converter. Have you already watched the? I mean, you should have already watched the video of lectures of this week. I will quickly draw. You tell me first whether if you have any doubt from this push-pull converter. Workings are already explained in the lectures, I believe. Ah, I did not draw the switches. If you have any doubt, do you have any doubt? Have you watched the videos?
Yeah, yes, sir.
Okay. So you tell me one thing. Uh, have you, or I mean, say in forward converter, we need reset circuitry, right? Here also we have a transformer. Four winding transformer is there. Don't we need a reset winding here? Reset winding of push pull has not been discussed in lecture anywhere, because it is not required at all. But can you can you explain why? Why do we not need a reset winding in a push pull converter? Okay, we will try to answer that question from the magnetics point of view. Okay, because there are four windings here, at least two primaries, so where to draw the magnetizing winding, that might be confusing. So let us look at it from the magnetics point of view. Okay, so I will draw this thing I discussed during the forward, not forward, flyback converter also, that if you are confused about the polarity of the voltages and currents in case of DC-DC converters, simply draw the magnetics and the windings with proper sense, so that the dot conventions you can put on them, then draw the rest of the circuit, so that you can figure out the voltage and current polarities. Yeah. Now if I draw the windings like this, you will see that dots will come in this fashion. You can verify it later. Okay. Now this is one switch. This is another switch, and these all, sorry, these all are grounded with together. Like this. Yeah. And this is a real transformer. Real transformer means it has a finite magnetizing inductance and it does store energy in its core. Now we will not need the secondary though for the explanation, but I will still draw it for the sake of completion of the circuit like this. Okay, right. So how is it operated? First we turn on S1, right? We turn on S1 first, then we give a blanking time here, then we turn on S2, another equal blanking time, S1 S2. They're turned on like this. Now this is the time when S1 is turned on, the core stores energy. Okay, the core stores energy. Mm, so we will look at the direction of flux. So when S1 is turned on, how, see, the current flows like this. So the current flows like this, flows like this. This is the core. So if you do right hand screw rule, if you apply, then the flux flowing through the core is in this direction and it increases. So if you draw the core flux, it increases. Okay, 0. Now at this moment you close S1. Now what will happen? See, the circuit that I have drawn here, this exact circuit, this will not be able to reset the stored energy in the core. Now the actual thing that we will have is a, sorry, say maybe a MOSFET, right? So it might be like this. So MOSFET, and a MOSFET comes with a body diode, right? Here also the same thing. I am just drawing the diode, otherwise I have to draw it once again. This is the diode I am drawing. So just know that to reset the stored energy, all we need is a diode like this. That may be a MOSFET that comes with a body diode, or maybe you will need to connect a diode if the switch that you are using doesn't have a body diode. Now let us see what will happen. So the flux was in this direction and it was increasing, right, when the switch S1 was on. Now we have turned on S1. We have turned on S1, turned off S1. The flux is still flowing in this direction, but since we have turned off S1, the current has suddenly stopped, and this flux now tries to decrease. Now if this flux tries to decrease, what will happen is all these windings, they will induce some current in them that will try to maintain this flux. Okay, so all the windings will try to create a current so that a flux flows like this. So that current I will draw in all the windings that they will try to create. Okay, so this will draw like this only, this winding, say winding 1, winding 2 will also try to have a current like this. So
Sir,
this flux I am drawing, just let me complete. They will yeah try to create like this, and it will try to create like this. Now what will happen is, this if portion, if you see, this current is like this. So basically the stored energy will get reset through this diode. If you do not have a diode here, then the switches will be damaged. But if you have a diode, which you generally have in practical converters, these parallel diodes, then what will happen is that the stored energy will flow back to the source through this diode. That is why we do not need a separate mm, reset winding in case of a push-pull converter. Yes, go ahead.
sir, when the flux in the core is flowing because of the current in a single winding,
Hmm.
uh, the currents in the other winding will try to keep the flux in the same value.
Yes, Lenge's law.
Okay, so according to that, the currents in the windings will be induced.
Yes, because the flux was trying to reduce, and Lenge's law said that the windings will try to oppose that.
Mm.
To oppose that, this kind of voltage will be induced in this winding, which will forward bias this diode.
Yeah, so it opposes the decrease. So, which means
Yes.
it tries to increase this flux.
Yes, at the end the flux reduces. At the end the flux reduces, but it reduces like this.
So, and the other one is about with this dot convention.
Hmm.
Uh, Sir, if I see the windings on the left limb, looking from the top, this looks like in anti-clockwise direction.
Hmm.
Whereas the right side, the winding on the right limb looks like clockwise direction. So since the windings are of opposite, that is the sense we are talking about, right, sir?
Did you get this anti-clockwise clockwise in some book?
Ah, yes, sir.
Which book?
Not in books, sir. Some source, online source only.
Online sources. Okay, let us see. Let me draw. Okay, you can mute yourself. Let me just draw two windings. Okay, one winding here, another winding here. Okay, now how to do dot convention if I have a drawing. So first I will start by putting a dot here. It does not matter where I put the first dot. What matters is relative to the first dot where I put the second dot. Okay, now once I have put the first dot, other dot I cannot put arbitrarily. Or if I have many other windings there also, I cannot put them arbitrarily. Okay, now I have a current flowing like this. Okay, so this current will create a flux like this, which will link this coil like this. True. Now if this current I, if this current I is increasing, then the flux is also increasing in this way. Now if the flux is increasing, suppose I have a load, it doesn't matter if I have a load or not, but suppose I have a load. If the flux is increasing in this fashion, then the secondary will try to have a current which opposes the increment of the flux. That is, it will try to create a flux in this direction. In this direction. So to do that, it must induce a current like this. So when an increasing current is coming into the dot terminal, I am getting a positive polarity in this terminal. So this must be the dot. Now check.
Yeah, okay, sir. Uh,
Wherever that clockwise anti-clockwise thing was discussed, I suggest you not to open that website ever again.
okay.
Okay,
Mm.
it's a democracy, anyone can write anything, but not everything is true.
Okay. This, so if we see if the flux increases, then the other windings will try to decrease the flux. So
Simple
in that,
Lenz's law.
yeah, then so okay. Mm.
And I believe I discussed this thing at least twice in this session previous classes, and you are quite regular also, that if the current entering the dot terminal is increasing, then all the terminals that are inducing positive are dots.
Uh, yes, sir. But there are other sources I referred and I got confused. That's why I'm asking again.
Just follow this one.
Okay.
Should I write? So if the current entering the dot terminal is increasing, then all the other positive terminals are dot terminals. There may be thousands of ways of explaining this. If you are confused, simply use this. If it is matching, then that is correct. If this is not matching, then that is wrong.
Okay. Okay, sir.
Yeah. Yeah.
Sir,
Yeah.
sir, in the if you see the flux in the forward converter and the flyback converter,
Hmm.
sir, in forward converter we say we are using the core as a transformer, so the flux will come to zero after every cycle. Whereas
If
in
you have set the duty ratio and the number of turns properly.
yeah, if you say the number of turns of the primary and the tertiary winding are same,
What was that formula?
no,
Derived
sir.
some time back. You remember? Should be somewhere here. N3 by N1 equals 1 by D minus 1. Yeah.
Sir, yeah, in forward converter we say this, and in flyback converter, the flux will not come to zero. It will come to some minimum value after every switching cycle.
That depends how we were designing, but that is how we design.
Sir, my question is, we say the core in the flyback converter stores energy, and in the
Hmm.
forward converter it won't store energy.
Hmm.
Sir,
Ideally, it doesn't.
ideally, because LM is infinite.
Yes.
Right. Sir, at that, mm, sir, we say the store flyback converter to stores energy.
Hmm.
Are we referring to that minimum value, a minimum flux that the core is attaining every switching cycle? Based on that, are we saying uh, half Lm Im square? I,
Um,
I,
I can understand
They
your question. What is the question exactly?
actually the flux is linearly increasing, and then it comes back to some minimum value in flyback
Hmm.
converter.
Hmm.
We say in flyback converter it stores energy, the
Hmm.
transfer core stores energy. Sir, are we saying that energy storage is only with that minimum flux with that we are attaining? Some because when it reaches the peak value, the energy is half L into I max square.
Hmm.
When it reaches mean value, it is half L into I mean square.
Hmm.
So the energy storage referred to this half L into I mean square alone.
And no, say if you have a flux waveform like this in a flyback converter core, then this much flux is always stored in the core.
Yes.
This is always stored in the core. When you are closing the primary switch, this much energy is stored in the core extra. When you open the switch, exactly that much energy is sent back. Is
Yes.
sent to the load.
Yes.
So the thing is, this much energy unnecessarily gets stored. So why design it here? Design it here. Design it here. Or in other words, we always design flyback converter at the CCM DCM boundary.
So so the flux in the core of a forward converter and the flyback converter can be same.
Ideally speaking, they are the same. Not ideally, practically speaking, they are the same. But we, for a forward converter, we want this to be as small as possible.
The ripple, the peak.
The peak, yes.
Okay.
You can never explain a flyback converter by saying ideal transformer. In fact, the term transformer is not quite true for a flyback converter. If you look at Ned Mohan's book, he has clearly written inductor, two winding inductor in case of flyback converter.
Okay. So we are saying it stores energy only because it is giving the energy back to the load, giving the energy to the load in the next cycle.
No, no, it stores energy because it has an inductance. The transformer of forward converter also stores energy.
Yeah. So its permeability will be
But for flyback converter, we are deliberately keeping a large permeability and a large inductance,
mm,
because that is what we need. That stored energy is what we are going to supply to the load.
so the real difference is in the core material, is it, sir?
Uh, I'm not very sure about it, but I think say at least up to 100 kilohertz, 200 kilohertz, only material is ferrite, and there are powdered iron cores, those things. So it comes from the dimension of the core that you choose and number of windings that you give.
Okay.
But I think Professor Umanand discussed these things in one lecture, that what is the desired VH curve of the material for a inductor and that for a transformer. So if
Yeah.
you
Yes.
have like
Yes.
this and if you have like this,
Yeah. So the right one is the transformer, and on the right side is this is the transformer core.
the transformer,
400.
this is a transformer because you see BH, so B by H gives you the mu, which is mu naught mu r, right? So if you have, see in this case the mu, say if I write it mu 2, if I write it mu 1, mu 2 is larger than mu 1. So for the same dimension of core, your permeance is larger here. Your permeance is larger here. Mm, larger. So permeance larger means, say, this Lm, this is large.
Sir,
So
is mu
Lm,
two? Okay. Hmm.
so Lm large means you are approaching ideal transformer. Whereas this one for an inductor. So this kind of material I will want for flyback, where I can store more energy here.
Sir,
Hmm.
one more doubt on that BH curve.
Yeah.
Sir, when the BH curve, we say when the core reaches saturation,
Hmm.
in that range the inductance depends on the current, and
Yes.
then the permeability also reduces
Hmm.
compared to the core permeability, the
Hmm.
permeability drops much.
Hmm.
Sir, and then since the permeability so the flux change on the saturation region is less, so the voltage induced is also less.
The voltage induced is also less.
Yes, because the flux change is less in the saturation region for the change in current.
Okay.
So the voltage induced is very less compared to the linear region. Is it, sir?
I think, see, these conclusions and all, they depend on in what way you are saying. The thing is, if you have a BH curve like this
Mhm.
and the slope everywhere is mu, okay, and your inductance L is n squared mu A by L.
Yes.
Right? Now, until this, say ni, your mu is more or less constant. So inductance is more or less constant.
Yes.
Now from here, it changes with current,
Okay.
and after some time, say mostly it mostly changes with current in this region. After some time, it more or less becomes parallel to the BH curve of air.
Okay. Oh.
Just a minute. Yeah.
So BH curve of air also has some slope, some least slope it will have.
Yes, and that slope is given by mu naught.
Mm. Oh. So okay, when the permeability of the core, when the slope of this curve, BH curve reaches this curve, this mu naught slope, then it is sufficient to say that uh, the core reaches air
There
permeability.
is completely, yes, completely saturated.
Sir, sir, here only I have the doubt that we have for suppose we are using this core for an inductor V equal to L di by dt.
Hmm.
Sir, if we operate in the saturation region,
Hmm.
the inductance value definitely comes down, and
Hmm.
the voltage induced also comes down. Uh, then how to comment on the di by dt variation?
When you say voltage induced comes down, what do you mean?
But what I mean is that uh, this uh, the B value on this when the current in the H axis varies by a certain amount, the corresponding
See, the
change in
thing is
Q.
where you are, that depends on where you are operating, and in say what is the
In
range of your
saturation.
operation.
Okay.
Okay.
So completely in saturation,
S-
suppose.
Suppose I am operating somewhere here,
Okay.
but my circuit is like this. Say I have taken the inductance, resistance values and all everything such that at steady state the current, which is equal to V by R, it's flowing like this. It is some it is giving me an H such that I'm operating here. Okay. Now, what is the induced voltage at steady state? Zero.
Okay.
Now it doesn't matter where you are operating. Wherever you may operate, it is zero.
Yeah, in steady state.
Yes. Now suppose instead of this, if you are giving a, say, a voltage like this to an inductor, okay, to an inductor, average, say average of this voltage is 0, and if it is causing a current swing which is restricted inside this zone, then you will get a current like this. You will get a current like this. Okay. Now suppose if this voltage is so large and maybe this inductance was so small that it does not restrict the current swing in this, it, say, the current swings in this range, then say if this is your voltage, average voltage is 0,
Yes.
if this is your voltage, then how will the current look? The current will look like this,
It increases up to.
like this.
Mm.
This will be the current. Now why is the current like this? The current is like this because V is L di dt, right? V is constant. V is constant. L reduces as current keeps increasing. L reduces. So if V is constant, L is reducing, di dt must increase. The slope of current increases. The current rises faster. Faster the current rises, more it goes into saturation. More it goes into saturation, more is a decrease in L. More is the increase in slope. The current becomes like this, peaky. So the voltage, if I draw the voltage across the inductor, what is it? This is only the voltage of inductor. So I'm not very sure what you mean by saying induced voltage reduces.
Sir, sir, this B can be written as phi by A, right? This B on the vertical axis
Hmm.
can be written as phi by A.
Hmm.
So, which means this vertical axis instead of B can also be phi.
Yes.
So, this in the saturation region, the current is varying. Suppose from the vertical you have drawn the red color lines.
Hmm.
Suppose the current is varying between those two lines.
Hmm.
Then H is varying. So at that time, the corresponding flux on the B axis will vary between the uh, those two red lines that is intersecting with the vertical axis.
This much it will vary.
Yes, sir. Uh, yes, sir. Not up to vertical zero, up to the first red line.
No, why first red line?
Uh,
My current is touching 0 every time.
okay. So then the flux will always be varying.
Yes. Flux will vary in any case. If the current
Yeah,
is
yeah.
varying, flux will vary.
Flux will vary. As far as the flux is varying in the linear region, we will have something like this, the voltage curve
Only
that we
thing
have
is
drawn.
that if we're in linear region, inductance of the circuit does not change. Oh, yes, that doesn't change.
In saturation, the inductance drops. So for keeping the voltage constant, the current changes accordingly, di by dt.
Yes, yes. All right. So this discussion was clear about why we do not need reset circuitry for a push-pull converter. If we simply have these diodes, we do not need a reset circuitry. These diodes will uh, push the or let the stored energy flow back to the source.
Sir, and in that the energy in the bottom winding,
Sorry?
Yeah, the bottom primary side, the bottom winding is act as a reset circuitry when we are turning off
That is
S1.
because, yes, that is because it turned on S1. The next time when we'll turn this S2, next time when we'll turn on S2 and then turn it off, during this time, this diode will then help the current to flow back.
Okay, sir. My question is, while resetting,
Hmm.
uh, the voltage on the winding should be greater than the source voltage, right?
Hmm.
We should ensure that to make that happen.
You need not ensure that. Lenge's law ensures that. Suppose the voltage of the winding is not more than the source voltage. Okay.
Mm.
Then what is happening? Then this diode is not forward biased. Diode is not forward biased means the current cannot flow, reset current cannot flow, so the flux cannot reduce.
Mm.
Right.
Okay.
But the flux is trying to reduce, so that voltage will keep increasing. That voltage will keep increasing until this diode is forward biased. Because ideally speaking, this V equals L, not does not right. V equals d psi dt. This has theoretically, this has a capability of generating infinite voltage if you do not give a path to it. Right. So the this will induce enough voltage so that the diode is forward biased.
Okay. Sir, this same explanation goes for our forward converter reset circuit also.
Yes. Okay. So push pull converter we have seen. The next topology is, sorry, we do not have many problems to discuss today, only some one, two, three, and easy problems. Anyway, so this is the half bridge converter. Half bridge converter, we have half bridge, as the name goes, and the supply voltage Vin is split by using DC link capacitors, and it is like this. Mhm. So if I have, say, here Vn by 2, Vn by 2, same values of capacitors, S1, S2. Here also the same thing. If you have diodes, that will help this LM to reset through them. Suppose I have turned on S1. When I turn on S1, what will happen? Um, who will let the current flow? Like this, the current will flow in this fashion. It will go. So if I turn on S1, the magnetizing current is flowing upward, right? In this direction. In this direction. Now when S1 is turned off, this current will find a path through, mm, how will it find a path? It will find a path through this diode, will it? Yes. In this way it will find a path. So the reset voltage is Vin by 2. it will discharge this capacitor even more. Yes, the reset voltage is Vin by 2. Let us take the capacitors are stiffly holding the voltages, and the whatever stored flux was there, that will drop to 0. Any doubt in this converter? The problem with such converter is the drop in capacitor voltage. As you can see, when we turn on one switch, the capacitors only supply the power to the transformer primary, and since KVL says that Vin equals Vc1 plus Vc2, the capacitor voltages, then if there is any disbalance in voltage, the supply sends current to balance out that voltage. So the capacitors takes power supply from the source, and then they supply power to the primary. There is no direct current flow from the source to the primary, so the capacitor voltage that drop, mm, it will drop like this. If you see the primary voltage, what kind of primary voltage are we expecting? We are expecting a primary voltage like this. When the switch is turned on, short time negative voltage for reset, another like this.
So this is voltage across the LM.
Yes, primary. But since the capacitors tend to what is that called, capacitors
Discharge.
tend to discharge, you will see waveforms like this. You'll see, sorry, this will be there. You will see waveforms like this. So to avoid this, what we do is we go for a full bridge converter, where what we have in the primary is nothing but an inverter. What we have is nothing but an inverter. Again, you can see by yourself that if you have anti-parallel diodes here, that is enough to act as a reset circuitry. The magnetizing current will flow back to the source. Yeah, one more thing you see here, for both half bridge and full bridge, when you are turning on, this will operate just like an inverter. So if when you are turning on S1 and S2 together, then the magnetizing current is flowing like this, and when you are turning on S3 and S4, then the magnetizing current is flowing the other way around. That is, uh, the core is operating in both first and third quadrants. So that is why I told you at the very beginning that all of them are kind of same in from the magnetics point of view, that they operate in both directions, both positive and negative uh, values of B and H. Okay, any question from these converters? No question. Then we will directly go to these problems. Consider two converters A and B. Converter A is forward converter with demagnetizing winding, and converter B is a full bridge converter topology. Full bridge is this one. Both the converter has same values of input voltage, source, turns ratio, switching frequency, output inductor, capacitor. Power switch of converter A is switched with a duty ratio twice that of converter. Okay, so what is the ratio of peak to peak inductor current triple converter B? All right, so converter A is a forward converter, right? The forward converter, what is the relation? The relation is n2 by n1 d1. Say I am writing d1, and for B it is a full bridge converter. The relation is equals 2 times, sorry, n2 by n1, say d2. Now they are writing that d1 is 2 d2, right? Switch to d2 ratio twice that of converter B. So they have given that d1 equals 2 d2. So if I put it here, then 2 n2 by n1 d2. So basically they said that input voltage is same, and they have somehow told that output voltage is also same, right? Output voltage is also same. What is the ratio of peak to peak inductor current ripple? Now you see, for forward converter, let me draw the secondary quickly. Say this is the secondary, okay, the secondary. Now when the inductor is turned on, what is the voltage across it? The voltage across the inductor is thus voltage reflected here minus V out. And for this full bridge, it's different. There are more windings, but operation wise they are same. When any of the windings are operational, say the upper one or the lower one, here also during the on time, the input voltage, sorry, the inductor voltage is n2 by n1 v in minus v out, right? So now see, for both the cases we have been asked to find out peak to peak inductor current ripple. So if I write IL, so this increment, what do we have? We have V L equals L delta I by delta T. This increment is dependent on these three things only: the voltage, inductance, and time, right? Now voltage is same for both the cases. We have seen that because V in is same, V out is same, inductance is same, they have said in the question. So all it remains is time, right? So the inductor which gets more time for this current to rise will have larger current ripple. Now you see, in this case the on time t1 is d1 ts, that is 2 d2 ts, and for this case it is d2 ts. Ts is same because they have said that switching frequency is the same. So basically the um, current in the inductor for the first case, that is for the forward converter, that increases for twice the time, is twice longer than that of the full bridge converter. So clearly this will have a current ripple twice that of the full bridge converter. So what is the ratio? Ratio is 2. A forward converter in this case will have a twice current ripple in its inductor compared to the full bridge converter. But do not take it as a statement. This problem has given so many things to compare between these two converters, which gave us this result. But do not take this as a statement that forward converter inductor current is twice, current has twice more ripple than that of a full bridge. With these many things, it does. Clear? Okay. The Paraltronic switches of a push-pull converter are switched at 50 kHz with a duty cycle of this much. It is supplying a 48 watt load. The turns ratio of the center tap transformer is this. DC link of the full bridge converter is from a 12 volt battery. Considering flat topped current, ignoring the ripple. What is this current? Okay, so they said considering flat topped current, but they did not mention which current to be considered as flat topped output or what. Um, but anyway, we'll uh, draw the waveforms and see. Push-pull converter, I think by now you can recall the converter circuit. I will copy. This is a clean diagram. So have you understood the current waveform through the diodes in case of a push-pull converter? Kind of unusual. Have you understood?
Not sure, sir.
Sorry?
And not sure, sir. Please.
Not sure. Okay. So say, okay, you can mute yourself. Say this is the time when one of the switches is on. This is the time when both are off. This is half time period. This is the time when the other switch is on. Again, both are off. This. So we'll draw this much only. One time period is enough for us to understand. Or should I draw two? Okay, let me see. So these are the switching. Now if I draw inductor current IL, okay, IL if I draw, see when the switches are on, the voltage either diode D1 conducts or diode D2 conducts, and basically inductor gets energy from the supply through the transformer. So during this time, current of the inductor will be rising. Current of the inductor will be rising. We have no doubt about that. And if the current of the inductor is rising during this time, we are studying DC-DC converter for long now, it must be reducing in this time. So you see, it is like this. Now I will draw the current in diode D1 and D2 also together. Okay, so okay, I have to name someone S1 and someone S2. Let me check if I turn this on. Okay, I will call this one as S1. Okay, S2. Why I call this S1? You see, when I close S1, I have voltage like this So I have voltage like this, so diode D1 flows. So when I have S1 on, D1 flows, D1 is on and the current flows to D1. So whatever current we had, whatever inductor current, the same current will flow through ID1. I will name these currents, okay. Say I will say this peak value of inductor current is I2 and this minimum value of inductor current is I1. If so, then this is I2, this is I1, because the same current is flowing, same inductor current is flowing through the diode ID1. And at that time we have this kind of voltage in the other winding in the secondary, and that is stopping D2, that is the reverse biasing D2. So D2 will not carry any current, D2 will be 0. Now S1 is turned off, so both the switches are now turned off, so the inductor current will drop. Now how will the inductor current drop? You see, inductor current will come back here and it will get divided, because both the paths are ideal, both the paths are identical, so it will get divided. Not only that, you see, in these two windings, say, let me name the windings, okay, 1 2 3 4. You see, in windings 2 and 3, in winding 2 a current is going out of dot, winding 3 a current is coming into dot, and the values of the current are the same. That is, the mmf of these two winding, they are balancing each other and cancelling out each other. So this reset of or this flow of inductor current through the transformer windings, that does not cause any change or any disruption in flux in the transformer core, because flux of one winding is cancelled by that of the other. And now if you see the diode D2 current, so it was carrying the full current, full inductor D1 current, say full inductor current D1 was carrying up to this, up to this. Now at this point, after I turn off S1, the current is suddenly halved, because it is now being shared between D1 and D2. So current is suddenly halved. So from I2 it jumps to I2 by 2, and the same I2 by 2 sounds nice, I2 by 2, the same I2 by 2 flows through the diode D2 also. And so basically this current, I will mark it once then erase. This current, whatever we have here, this falling current, that is divided into half between diodes D1 and D2. So like this and like this. So what is this amount? They become somehow different in this two. Anyway, so this, okay, this much is I1 by 2, and this much is also I1 by 2. At this point S2 is turned on and the inductor current again starts increasing. But you see, when S2 is turned on, the inductor current is suddenly or the inductor current is switched to D2 completely. That is, whatever the inductor current is now, that much is the diode current I22 D2. So the diode current will now jump to I1 from I1 by 2, I1. Then it will follow the inductor current I2, and during this time ID1 will not carry any current. At this time, when S2 is turned off, again the same thing happens. It drops to I2 by 2, again I2 by 2. Oh, I2 by 2 was here. It drops to I2 by 2 and reduces like this. And here also it comes to I2 by 2 here and reduces like this. So basically mm, when the switches are turned off, that when both the switches are turned off, that is during this time and during this time, the falling current is divided into half in both the diodes, and during the other times when S1 or S2 are on, either D1 or D2, depending on which one is on, carries the full inductor current. That is why the diode current looks like this, kind of unusual. That's why I asked you whether you understood this diode current waveform. All right. So in this question, you see they have not mentioned the value of inductance. Everything else they mentioned, but they did not mention the value of inductance. And they want us to find out RMS current of the secondary diode. So unless the inductance value is mentioned, I mean this inductance, we cannot find out the slopes and all. So what you can say that when they said flat topped current, they meant the inductance value is so large that the inductor current is flat topped. Now if the inductor current is flat topped, say, just a minute, if the inductor current is flat topped, then what is the value of the inductor current? You see, this is a buck converter. After the inductor, only the capacitor is there, and the average current of a capacitor is 0. So whatever the load current, that much is the inductor current, right? So if the inductor is carrying a flat topped current, that must be the load current. So what is the load current? 48 watt load. Have they mentioned anything else? Output, can we find out somehow?
Turns they have mentioned.
That is a secondary. What is the primary? Oh, okay. Turns ratio is 5. No, what does it mean? Turns ratio is 5. So this whole thing by this whole thing is 5. Oh, okay. I think what they mean to say is it is, but is it 1 is to 5 or 5 is to 1? See, we'll solve this question, but I advise you when you are writing maybe your report or thesis or making questions for others, do not make this kind of statements. Okay, these are very much vague, and there is no such convention that when I say turns ratio it is n2 by n1 or something. Okay, never do that. These are very much vague convention, vague statements. Anyway, we will do something. How to do? I will take, say, 5 here, 1 here. Okay, I'll take 5 here and 1 here. So if I do that, then what is the output voltage? Output voltage will be 2 times 2.5 times mm, input voltage. What is input voltage? 12. So 60 volt. 60 volt is the output voltage, right? You understood why I wrote 2.5 here? The V output by V input, when you write N1 by N2 times D, this N1 N, sorry, N2 by N1 times D, this N2 N1s are nothing but this N1. This N1, this is N1, this is N2, this is N2. Then only you can write this, okay? So for this case, this 2.5, 2.5. So that's why I wrote 2.5. Okay, so it is 60 volt, and 60 volt it is supplying some 48 watt load. So what is the load current IL? 48 by 60, 4 by 5 ampere, which is 0.8 ampere. Yeah. Now, if my inductor current is 0.8 ampere and it is flat topped, what is happening? What should be my diode current? Say I am drawing the diode current of D2, okay? Just match with it. D2 I am drawing. So during this period, it is carrying the full inductor current, which is 0. Okay, let me not write like this, which is 0.8 ampere.
D2. Yes.
D2. I am drawing it because this waveform somehow comes full here and is ID1 is broken. I could have drawn another cycle also here, say like this also I could have drawn. Okay, anyway, I am drawing for D2. So point 0.8 comes, no question of rising or falling of anything because it's flat top, so only point 0.8 and 0.4 ampere for this duration when both the switches are turned off. So the diode current looks like this, right? This is one complete time period. So what is the duty ratio? Oh, I did not mention multiply the duty ratio. Sorry, I did not multiply the duty ratio. I wrote it here. Duty ratio is zero point 0.4. Sorry, 1 by 4. So it is 15 volt. 48 by 15. Mm, 16 by 5. So it should be 3.2 ampere. In this equation, I forgot to multiply the duty ratio. So it is 3.2 ampere, 1.6 ampere. Now we have been asked to find out the RMS current of the diode. Okay, we already know the waveform. All we need to know is the duration, for how long it is, how much. So it is 1/4. So this is T by 4. This is, no, not T by 4, 1/4. Just a second. When they say 1/4, this is T by 4. Yes, switching a duty cycle of one switch is 1/4. So this is T by 4, true. This is T by 4. This is T by 4. And this duration is T by 2 minus T by 4. So 2T by 4, again T by 4. So now we can find out the RMS of the diode current. You want me to do this? Or you can do this?
We can do it.
It's easy, no? Just, okay, someone said yes, said do it. So it's this much current squared times the duration. So say I am writing I as 3.2. So I squared by 4, that flows for T by 4, right? Happens twice. I squared by, sorry, I squared flows for T by 4. So it comes out to be I squared by 8 plus I squared by 4. Uh, 3I squared by 8. So the RMS becomes id. Please check if I am doing some mistake in calculating RMS. Then that will be a blunder. id RMS is nothing but square root of 3 by 8 I. Whatever it is, it is. This is correct, no? This part. Okay, is it clear? This waveform was clear, how I drew this waveform?
Yeah, yes, sir. Sir,
Yeah.
sir, can we draw the flux in the core? Sir, actually, when the currents are equal dividing,
When?
when the inductor is discharging and both the switches are off, at that
Hmm.
time the equal current is distributed. Equal current is flowing through the both the secondary.
Hmm.
So at that time, fluxes are opposing in the core.
Yes, so they cancel each other.
Sir, they cancel each other. The total flux in the core will become zero.
Uh, if you say, if I talk about an ideal transformer, that is anyway zero. Okay,
Uh,
the flux in the core is anyway zero. What happens in ideal transformer? When there is no load, the primary draws no current from the source. Okay, when there is some load, the load draws a current and the primary also draws a current, and those two currents create equal opposite flux. So
mm,
ideal transformer has no flux flowing through the core.
uh,
Practical transformer, it has some flux flowing through the core depending on the magnetizing inductance. But then
yes.
again, if you have a load, the load draws some current and the primary draws some current with the ratio n1 by n2, such that those two fluxes cancel each other. So the value of flux remains the same. The full load flux, no load flux, they are the same for a real transformer, practical transformer. Now for this case,
Mm,
when I said, now this case, what is happening? Say we are talking about an ideal transformer. There was anyway no flux flowing through it, and when the inductor current was reducing through the secondary windings 2 and 3, they are also not giving any net flux to the core. For a
so equal and
practical,
opposite.
yes, there means the magnetics of the transformer is not disturbed uh, by the inductor current of the secondary.
Sir,
Yeah.
shall I ask the question?
Yeah, sure.
You have drawn the wave shape of I1. Okay.
I1,
Uh, I1 that I1.
ID1. I1 is the value
Ah,
of this.
okay. Current flowing when D1 is conducting.
Yes, ID1 and ID2 are the
Ah,
waveforms.
the two waveforms. So I1 is a shape is triangular with some that is ripple current and with the DC bias. So again, the DC bias is going to give some B field in the transformer.
No, no, this current,
BDC,
this is this currents,
huh,
this current and this current.
huh,
So if you look at say this duration, say in this duration and in this duration, if you look, then
huh,
the currents flowing through the windings are same but in opposite direction,
huh.
so they are not creating any flux in the
What's it ampere?
uh, yes, their net ampere turns is cancelled by each other, so they are not giving any net flux to the core. And if you look at the other times, that is when, say, this time when the switch is turned on, say S1 is turned on, then what is happening? S1 is turned on means, say here, this current is flowing, and this current is a linearly increasing current, and that
Yes.
linearly increasing current is reflected here in winding number 2, this one. So those
Okay.
two currents, they are balancing each other, just like any other transformer operation.
Okay. Okay.
Sir,
Yeah.
in the primary side now, if we want to draw the magnetizing inductance,
Hmm.
how to draw that, sir? Do you want to?
Yes, I was thinking, but see, when we say magnetizing inductance for any transformer, so when you draw the what is that called, equivalent circuit and all that, we draw the magnetizing inductance um, referred to one side, right?
Yes.
We draw it referred to one side, so we can draw it from any side. So what I think, if you have to draw, say when S1 is on, let me see if I have it still in my clipboard. Yeah. Say, I'm not very sure about the explanation, but this might be true. When S1, say this was my S1 and this one S2. When S1 is on, this magnetizing, we can talk about magnetizing inductance, and a current was flowing through it, and that is basically representing the stored energy in the core. Now, when we have turned off both S1 and S2, what we can say is, you see, at this time, we can consider the magnetizing winding is not here, rather it's here.
Hmm.
How can I say that? That is because at the end, all the windings are put on the same core, and the magnetizing winding current is nothing but the flux, and all the windings are seeing the same flux, right?
Ah, yes.
So I can say it in this fashion, that it is here
Mhm.
and it is giving back its current
Stored energy.
stored energy like this. This can be one explanation. Another explanation can be like this: if you are not comfortable with taking magnetizing current once here, once there, magnetizing winding once here, once there, then I think this explanation should also work. Let us keep it here only. We turned on S1, current was flowing like this, then we turned it off. So it will have a path like this to flow. But now, after the magnetizing winding or magnetizing, say this XM, after the magnetizing inductance, what we have is a real transformer. So if there is a current flowing through here, it must get reflected in some other winding, right? Now,
Yes, sir.
you see, this is reducing. This current is flowing like this, and it is reducing. Okay. So if I
Okay.
write this as V, V is L di dt, and if I is reducing, so V is negative. So dot is negative. So basically, you see, this will induce an EMF like this in this winding, which
Mm.
will induce a current. So this is nothing but you remember that explanation of our reset winding,
Okay.
just
Yes,
like
sir.
that, is just this current was stopped, but this current keeps circulating, so this induces a voltage here, and that pushes the power back, the stored energy back to the source. This way also we can explain, I believe. This polarity is clear, no? How I got this will be plus, this will be minus.
Yeah, yes. Got it. Sir, in the next cycle, it will the inductor will be on the bottom side itself. It will store the energy.
uh, just a minute. Next cycle, again I think if you have to explain it in this way, that I turn on S2, so I have a voltage like this. This is an ideal transformer, so this voltage will be reflected everywhere, so in this winding also. So let me clean up some things and draw it once again. So this means negative at dot, so it will induce a voltage here also like this. And yes, you see, so basically what is happening, when you close S2, this current I has two components. One is the load component, other one is the reflected magnetizing current component. So the magnetizing current is flowing here, which is storing the energy. Okay, S2 is closed, and that being reflected here is flowing through this winding. In this way also we can explain it in the next cycle.
So,
Yes.
sir, here
Yeah.
at that time it is going to reset the core.
No, it is not resetting, it is increasing.
No, first half cycle it is going to set by the first winding. Then next winding
No,
it
not
is going
first
to
half
reset.
cycle. When during this time when S1 is on, energy is
When
stored. When both
stored.
are off, energy is sent back completely. Again when S2 is on, energy is stored. Again when both are off, they are sent back completely. This whole thing makes one complete time period.
Okay. When the both the switches are off, that time it is getting reset.
Yes, yes. Uh, since he asked about how to draw the magnetizing winding, I am trying to explain that I will keep it here only. And by that, if we can explain the storage of energy in the core, apparently we can.
Mhm.
We can. You understood the explanation, no? How it will look like when S2 is closed.
Yes, sir. Sir, if you, if it's possible, please repeat again, sir. Please.
Okay, I will draw it here once again. I will draw the inductance here only.
Okay, sir.
Okay. You see, just forget this for some time. What happens, say, for a forward converter? If you have inductance, magnetizing inductance here, so when you are closing this switch, this branch is drawing the load component of the current, and this branch is drawing the magnetizing current. So the total current that you have is the load component plus the magnetizing current, right?
Yes, sir. Yes, sir.
Now,
Yes.
now look here, look in this circuit. I am closing S2. Okay, so I am getting this kind of polarity here. Now, this kind of polarity will appear everywhere in the transformer.
Yes.
Appear everywhere in the transformer. Now, if this polarity appears across the magnetizing inductance Ln, that will create a current that will cause a current to flow like this.
Yes.
So how is the what is the current path? It is flowing through this winding, no? Means through the ideal transformer, right? So if I call it Im, and since I have N1 and N1 equal, if they are unequal
So
also it
it's
doesn't
not
matter.
audible.
Can you not hear me now?
Yeah.
Yes, sir. It is
Now we
audible
are
only.
hearing
Oh, okay,
audible. Now it is audible.
okay. So we have in any case here N1 equals means they are equal. Even if they are not equal, the current that was flowing here, flowing through the magnetizing inductance and then through the winding of the ideal transformer, that will be reflected in this winding, so this winding will now carry load component of the current at the same time, a magnetizing component of the current which is reflected. So it is possible to you know explain the thing by keeping the magnetizing inductance anywhere. You remember, no, this thing today also we said once that if I have a two winding transformer, if I keep one winding open, it just, and for the other winding it is just an inductor.
Yes. Yes.
Suppose, see, suppose I have n1 turns here and I have n2 turns here. The permeability, sorry, not permeability, the permeance or reluctance seen by both the windings are same, right? So L of this winding is n1 squared permeance, and say I write L1, and L of this winding L2 is n2 squared permeance, same P, right? So basically, why I am saying this is, if you are trying to draw the equivalent circuit of this transformer, you can draw the magnetizing inductance on the primary side on the one side, then it will be L1. You can draw it on the other side also, then it will be L2. And if you see, L1 by L2, which is nothing but x1 by x2, is simply n1 squared by n2 squared, which you have already studied in transformers, right?
Yes, sir.
So basically it's just from which side you are referring to. Yes, Nilesh, please. Nilesh, you can go ahead. Nilesh, if you are saying something, we can't hear you. You can use the chat box. Okay. Anyway, we'll go to the next question. By that time, Nilesh, you can keep writing your question in the chat box. I will get it. A half bridge converter circuit is shown below. Switches are operated at duty ratio 0.3. What is the output voltage of this circuit? Sir, I want assignment of this year with solution. Is it possible, sir? I believe they release assignment solution of every week, don't they?
Up to
Yes.
assignment 9 it is over.
No, I am asking about solution. They're releasing the solutions also, right?
Yeah.
Yes,
That
up to assignment 9 it is over.
Yeah, okay.
cum-
No,
cumulatively for 3 weeks they are releasing, sir. Every 3 weeks.
every 3 weeks, then you will give, you will get. Obviously, you will not get it before submitting. Once you submit, the deadline of an assignment is over. After some time, they will give, I think. But should I enroll with courses in previous? Eh? I enroll with courses, yes, so. Um, Nilesh, I think this technical things I am not. You can directly talk to the course TAs. There must be some forum. I am not a direct course TA. I just take these classes. A half bridge converter is shown below. The switches are operated at duty ratio 0.3. What is the output voltage? Okay, so for half bridge, the output voltage is input voltage times N2 by N1 D, right? What is input voltage for T8? What is N2 by N1? See, it is 1 is to 1. N1 by 2 N2 is 1 is to 1. So it is 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0.5. 0 right? It is 0.5, yes, times duty ratio. What is duty ratio? 0.3 or 7.2 volt. 48 half 24 72 7.2 volt. What is the average value of current in ampere flowing through the magnetizing inductor of transformer under steady state? We discussed this some time back. Half bridge converter, and there are diodes also anti-parallel to the switch. So the magnetizing current, the magnetizing inductance has path to discharge. It will discharge through the diodes and through the caps. So it will look like this. Magnetizing kind of look like this: increase, then drop, maybe stop for some time depending on the ratio, and then again increase. Sorry, increase, drop, and these two will be identical. So average value of current, magnetizing current at steady state will be 0. We do not even need all these things. It will be 0. What is the peak inverse voltage experienced by the diodes? Okay, so when does a diode experience peak inverse voltage? When it is off. So maybe we will take the situation when D4 is off. So D4 is off. D4 is off means D3 is conducting. There is no situation where both of them are off. So if D4 is off, then the circuit looks like this. This is inductor, one winding, other winding. This is our D1, which is short circuited. I'm not drawing it. This. So this voltage we have to find out. Here is our D2. This VD we have to find out. So see, in this situation, definitely S1 is closed. That's why D3 is conducting. So N1 must be getting a voltage of 48 volt. Okay. So 48 volt means N2, this whole thing is now getting 48 volt. So this voltage is 48 volt, and clearly this, in this loop, if you apply the KVL, you will get VD is 48 volt. So the peak inverse voltage is 48 volt of the diode. Clear?
Yes, sir.
Yeah. Okay, one last thing I wanted to say, just came to my mind while writing this. See, look at this waveform, this waveform and this waveform. Okay, switching waveform. Say S1. Okay, what I have drawn here is one complete switching cycle. One complete switching cycle. After this thing, the switching again repeats itself. So the switch S1 is turned on for this time, it is turned off for this much time, and it is again turned on here. S1 is again turned on here. So the frequency of switching is 1 by T. But now if you look at the inductor current, what is its frequency?
It is 2 times that F.
So frequency of inductor current is 2 times.
1 by 2 T.
This is 2 by, not 1 by 2T, 1 by T by 2.
Okay.
So in this
2
time
times
period, it is repeating itself twice.
yes.
So basically you are not going for higher switching frequency, but still in your magnetics you are getting higher frequency. So higher
So while designing,
just a minute. So higher
so,
switching frequency, we have seen that is associated with higher switching loss. So we are avoiding that, but still we are getting higher frequency current in the inductor. So our inductor size is reduced. Okay, so that is one advantage of it. Our inductor size is reduced. Yes, you are going to saying something, Mr. Derkar.
Huh. Sir, if the switching frequency, inductor frequency is two times the switching
Switching
frequency of
frequency.
the S1, yes.
Yes.
So the size is going to be the half of the normal forward converter type of
Yes.
inductor.
Yes.
It is going to benefit there.
Now you might argue that, but I have a large transformer here. But I will give a counter argument saying, um why not use a full bridge converter? Then your number of windings are the same, because in forward converter also you have three windings. You have to have a reset winding. Full bridge
Yes.
also you have three. But again, you can give me a counter argument that there are more active switches. Okay, then I will again give you a counter argument that switches do not take much space. Magnetics take more larger space. Okay, that's all then for today. Next day is gate driver. Maybe I will discuss about isolation. Some first or second class of this course, I told you maybe that if there is time, I will discuss about isolation, why isolation is required. Not a very large discussion, very small discussion, but I will go through it. Isolation, because gate driver isolation is important, and what kind of
Sir,
isolations are there. Yeah.
sir, the recent trend is that SiC MOSFETs are coming.
Yes.
So the gate drive of that is not discussed in sir's lecture. So can you address that?
The thing is that
Uh,
SiC MOSFETs are kind of advanced thing. Even I do not know. I have colleagues here who are working on SiC MOSFETs, but that is quite. I have no idea about that. And this is a fundamental course. Do not expect SiC MOSFET gate drivers being
Cool
discussed.
SiCs are coming, and
Yeah, I am not the right person to ask this question. That's not my specialization. I'm
gate
sorry.
drive of SiCs not
No,
not.
no,
Okay,
no, no. I have no idea. Those, I mean, there are people who are doing PhD on it here.
okay.
I think, I mean, that's not my area actually. I work in machine design, not much idea with SIC.
Less like Coolmos, the cool SiCs are coming, so they're cost competitive also.
Okay, but I don't have idea about it.
Okay, okay,
Okay, then that's all for today. Thank you.
okay. Thank you, sir.
Sir,
Yeah,
sir, sir, only one question. In the
yeah.
sir, especially in the forward converter, which you have discussed earlier,
Hmm.
in the primary and third winding, sir, if
Hmm.
the third winding turns is large compared to the primary winding, then uh, actually we can go beyond zero point 0.5, is it, sir? The duty cycle can be go beyond zero point 0.5, is it? Hello, hello, sir, am I audible?
Yes, yes, I've heard you. I'm thinking. Yes.
Uh, Similarly, if N1 is larger than N3, then we can go only less than zero point 0.5.
Yes. But the thing is, since this is a kind of buck converter, it's just an forward is just an isolated buck converter, and I discussed this one day. No, that
Yeah.
we cannot go for very large boost or very large buck. I mean, those are restricted
The gains.
gains. Yes, the circuit non-idealities, they start dominating beyond some ranges of D. I do not think people go for that. Okay, since you said this, I just remembered one more thing. There is one IC called SG3524. Mm, what it does is, inside it generates a triangular wave whose frequency is decided by you only by connecting some RC network outside, and compares it with a zero point 0.4. No, sorry, this peak of the triangular is most probably 0.4, and compares it with some voltage. This, if you compare it, you will get, you know, waveforms like this. This is a common PWM generation method, and this voltage level you can vary from outside using a port, and hence you can vary the duty ratio, and the frequency you can change with an RC network connected outside. Why I'm saying this is, this has two outputs. Okay, this IC has two outputs. If one output generates a waveform like this, the other output simultaneously will generate a waveform like this. So if you match it with this switching waveforms, you can see you can drive these two switches using one IC only, one control IC. One of it will go to S1, another will go to S2. Say you send this to S1 through gate driver, send this to S2 through buffer and gate driver.
Just there
And
is a gap.
as far as I know, means this does not go beyond duty ratio 0.4, some limit.
This IC is a this has some converter, sir. This IC.
Not converter.
It's just positioned this way.
16. There are 16 pins on it. 8 dual inline package. Somewhere here in pin number 7, 8 or 6, I think you have to connect the RC network, where which will decide the frequency. I think in pin 2 you have to give the voltage, which will decide the duty ratio. I think in pin 3 you get to see the triangular wave. You can get download the data sheet and see.
Okay.
10 and 11 I think gives you the output.
This is
VCC is somewhere here. Don't take it from here. Okay, I forgot. I worked on it much back. Just download the data sheet and see.
Okay. So this S1 and S2 are having some gap, which is some dead band we are trying to give.
Yes, because you have to give this inductor current some time to drop. You cannot let it increase and increase. Whenever S1 and S2 are on, the inductor current increases, so you have to let it drop also.
So it can be some T/4 on.
Yes. But when we say duty ratio, we say the duty ratio with respect to one switch only.
But since both the switches are operating with same duty ratio, we can say only one.
Okay, then that's all. I will stop for today. We will meet next Monday.
Good night, sir. Thank you.
Good night.